So the scale for the initial term is rho u squared divided by L for both inertial term. The scale for the pressure term is also rho u squared divided by L. Now when you look at this, you directly see that one of the two is going to be much smaller than the other, right? And you know, in a way you have a Laplacian. The first term, you know, scales with u divided by L squared, and the other scales with u divided by delta squared, and delta is very small. So you know that this term here is in fact going to dominate. Right? It's going to be much larger, and you see there's a 1 over factor, there's a Reynolds factor in there. So this term here is very small, right? And then when you look at the scale for the Reynolds number, so the value of the Reynolds number is rho u L divided by mu, then you see that the scale for this term here is also rho u squared divided by L. Now this shouldn't come as a surprise. It comes from the fact that you have the right scaling for delta. If we hadn't inferred physically the scaling for delta, you would not dimensionalize with an unknown length scale y or delta in the y direction, and the fact that this term here has to scale with the inertial term is essentially what we're trying to do. We want to determine the region where both the inertial term and the viscous term are relevant. So they need to be on the same order of magnitude. Okay. So here what you see is that it's the term which corresponds to shear. Right? It's the term which corresponds to the mu du dy, so to the shear due to the no slip at the boundary. This is the term that remains in the momentum equation. Is that clear? I mean, it shouldn't come as a surprise, huh? that this scale here now is the same as the others. This is how we design delta. We design delta, the boundary layer thickness, as the thickness where both the effect of viscosity and the effect of inertia will be important. Right? And therefore, you know, if this number here turned out to be much smaller than rho u squared divided by L, then we would have failed, because then that would mean that in this new region that we sort of determined now, the effect of viscosity are also negligible. Right? Yeah? Okay. So this is what we have. So now we can divide everything by rho u squared divided by L, and we are left with, in non-dimensional form, we're left with the following equation. We have, so the inertial term remains intact, it's still there, plus v partial u partial y, so here nothing has changed, is equal to minus partial p over partial x. The pressure term is still there, of course, and then we've dropped one term in the viscous term. Okay, so now we're left with second derivative of u with respect to y. Okay, so that here is the x momentum equation for the boundary layer. Okay. Let me. Now let's continue. We'll do the same in the y direction, except I'll do it faster. Right? So in the y direction, maybe this is a good idea. It will be a good practice. Sorry, what? Oh, I heard something. So for the y momentum, it would be a good thing for you just to practice non-dimensionalizing Navier-Stokes equation. So when you do it, yeah. Which one? This one here? Yeah. So this one here. So right from the here, it should be clear that this one is going to scale with that. The other one is going to scale with that. Yeah, but delta is much more than L. So you know that the one on this one is going to be much bigger. Yeah. Yes. All right. So we're left with these terms, and now in the y. Okay. So sorry, I was at the y momentum equation. For the y momentum equation, I'll let you do the non-dimensionalization, so you can do it yourself. And in the end, what you should get is 1 over the Reynolds number. So do it as an exercise. I think it's always, you have to do these things. I think, you know, from watching me doing it, you get an idea of how it works, but you have to do it yourself to really feel comfortable with that. So once you do that, you will get this minus partial p over partial y plus 1 over the Reynolds number squared as second partial of v with respect to y plus 1 over the Reynolds number and the second partial of v with respect to y. Okay? So you'll get to that, and now if you look, Reynolds number being large, this term now is small, this term now is small, so those two terms are still in the same order of magnitude. This is roughly what we had for the x momentum equation. This term is negligible compared to that one. That's the same analysis, but there is clearly one dominant term, and this is your pressure term. Right, so actually what you're left with is just at 0. All of the other terms are negligible in front of the pressure term, and you get to a first approximation that partial p over partial y is equal to 0. So in a boundary layer thickness, your pressure across a y section is uniform. That's an important result. Now, again, this is going to be, you're going to see something similar over and over again. This is not unlike what we've discussed, that when your streamlines are parallel, you don't have pressure gradients in the y direction. Right? So when you have a geometry where the flow field is almost parallel, then you don't expect much pressure gradients in the y direction. That's also what you have in the boundary layer. Okay? So this shouldn't come as a surprise, and in fact, when we'll do lubrication theory, when we'll do unidirectional flows, that will be exactly equal to 0 always. So we'll discuss that, and when we'll do lubrication theory, which is flow in thin films, again where you have you have flow mostly in one direction, you'll see again that the pressure across the streamlines is equal to 0. The pressure changes, so the gradient of the pressure across streamlines or in the y direction is equal to 0. So finally, now I'm putting the dimensions back because we'll solve them with dimensions. In the boundary layer, the terms that you really have left are, you have to solve for the continuity equation, and the x momentum equation simplified, you drop just one term. In the x momentum equation, we drop one term in the viscous, one viscous term. So this is, we're left with partial mu with the second partial of u respect to y. The second partial of u respect to x dropped. Right? That was the point of doing the non-dimensionalization. This is the momentum equation in the x direction. And the momentum equation in the y direction, that one simplifies significantly because it just reduces to partial of p with respect to y is equal to 0. Okay? And so you see that those equations have both effects of inertia and viscosity, but they're significantly simpler to solve than the equations than the full Navier-Stokes equation. But those are, of course, only valid in the boundary layer. So this is what we have. Do you have any question on that? So being able to get to the boundary layer equation, even though it is, it can be painful because you really have to be careful with keeping all of the terms in, but this is something that you expected to understand and to be able to do. Right? So being able to come up with the scaling for the boundary layer, being able to simplify Navier-Stokes equation in the case of boundary layers, that's all part of what you should be able to do. Now you can solve these equations. They're easier to solve numerically. You cannot solve them analytically. Right? So every solution that you will see in your book. So when you open your book, for instance, you'll look. Then after, so first you'll derive the boundary layer equations, and then if you go on from 10.3 on, you have different solutions, so different kinds of boundary layers, and cases for which you can solve it. The most important one is what you find in 10.3, which is the Blasius solution. Okay, so this is the one we'll discuss. Now, all of the others, you simply you have to be more of an applied mathematician to appreciate them, but because there are different cases, you use different methods to solve and to infer the solution of the velocity profile in the boundary layer. Now, one thing which is very trivial is the pressure profile in your boundary layer. This is simple, right? Because P here is constant across your boundary layer in the y direction. So you can identify your pressure outside of the boundary layer. So if you do have pressure, is the pressure imposed by the outer solution, right? So in the example that we discussed here, for instance, right, if you think of this as, it was here. If you think about an airfoil, right, there, what you would have, for instance, is you would compute the solution for the flow outside of a boundary layer using rotational flows. You get a pressure distribution, right? So you compute for the potential flow, get the velocity, you use Bernoulli equation to get to the pressure. Then you have a pressure distribution outside of the boundary layer, and that gives you your partial P over partial X. So you know what the partial P over partial X is from the outer solution, because partial P over partial Y, this is constant, is equal to 0, so the pressure is constant across the boundary layer. So across, in this direction here, across the boundary layer, your pressure is constant. Okay, so that already, if you're thinking about solving for those, so when we have to solve for this, the pressure field is already partly known, and partial P over partial X comes in at the very end of your it's sort of an input, knowing what the pressure gradient is from the outer flow. Then you already know what this is. So your pressure field is not difficult to solve. What you have to solve for is your velocity field and imposing the no-slip boundary condition. Okay. So what we'll do is we'll discuss the Blasius solution, and the Blasius solution is a solution to the boundary layer equations when there is no pressure gradient in the x direction. So when the flow is not driven by a pressure gradient. So this is really thinking about the flow on top of a flat plate. If you have the flow on top of a flat plate, there's no curvature, and therefore if you're solving for irrotational flow, then all of the streamlines are straight, and your velocity is just a uniform flow, right? A uniform flow with no pressure gradient. So that is the Blasius solution. This is what we're going to do. This is what we're going to do now, and I think by all standards, this is one of the most mathematically involved part of the class. So this is the Blasius solution. Hold on, I lost my ruler again. Oh, this. So, I'm not going to rewrite the Blasius. I'm just going to say roughly what it is. So the Blasius solution is a solution to the boundary layers in the case of a flat plate when there is no pressure gradient in the x direction. So for the flow over a flat plate, and the flow velocity outside of the boundary layer you can say it's constant in the x direction and partial p over partial x is equal to 0. Okay, so this is our flat plate. And when we did the Jankowski transform, I showed you a flat plate which is at no angle of incidence, and you saw that the velocity was uniform. And then the velocity is uniform, mu is equal to a constant. If you apply the Lewis equation, you know that the pressure is equal to a constant as well. Right? So the pressure is just uniform, so therefore you don't have any pressure gradients. So my flow here is uniform, and therefore the pressure is also uniform. Yeah? And so in particular in the outer solution, the important part is that partial p over partial x is equal to 0. So this is only for a flat plate. Yeah? And that's the easiest case, so this is why we'll discuss this solution. In other cases, if you have the flow around the profile, for instance, dp dx would not be equal to 0, and then solving the boundary layer equation is even more complex than what we'll do now. So this is the only case where I think we have a chance, and you have a chance to sort of understand and see how the solution works. So in that case, our boundary layer equation, they simplify to partial u over partial x. So sorry, u times partial u over partial x plus v times partial u over partial y equals to nothing. Right? Actually, I now realize I forgot a row here. Now that I see them, here I'm missing a row. Sorry about that. I just saw here that something was missing, and I realized it was missing before as well. So there is no pressure term plus mu second partial of u with respect to y. And then the other equation is just partial p over partial y equals to 0, but we don't have to do anything with this equation. Right? Essentially, we can just say that the pressure is equal to a constant everywhere. You can identify it at infinity. So the only two equations we have to solve are the continuity equation and the x momentum equation. Okay, so we'll solve those two PDEs. And now you have to realize that those are two coupled PDEs. So this is going to be complicated. Right? You've never seen in your regular, there's no simple trick to solve these. It's not ODEs already, linear ODEs you know how to solve. Special special ODEs for which there is a known solution, you also would know how to solve. PDEs, it becomes complicated. Laplace equation, we have some solution for that. This is why potential flow is such a great thing, because we have solutions to the Laplace equation. And now when you look at this PDE, there is nothing about this PDE which is trivial. Okay, so don't expect that you will be able to solve that. And I'm saying this because I still see oftentimes in exams, students just writing out the Navier-Stokes equation with the hope that you can solve it. Right? So I'm seeing like Navier-Stokes equation and integrating along the y-axis. Just forget this. There's no way you're going to solve that. This here, you can just photographically memorize this. This is complicated PDEs to solve. There's just no way you're going to solve that by first integrating in y, keeping x constant, and then it's just not possible. Mathematically, this is impossible. They become, if your equation is anything, if you have a PDE which is more complex than just the Laplace equation, then I wouldn't expect you to know how to solve it, right? Unless we already discussed a solution, or this will involve computers. This is already a complicated PDE to solve. So, but of course we are thankful to our method. So who is in applied math here? 1, 2, 3. So this is the one part of the class where I think you guys will feel most comfortable. We had some classes which were very comfortable for engineers, more for physicists. So this is maybe the one part where you're gonna like, yeah, I know this. Now for the rest, it might be a little bit overwhelming, but we'll still do it. Okay, so the first thing that we'll do is, so let's discuss, so this is introduction, let's discuss the solution. Right, here I forgot an equal to 0. One way of making the equation simpler and already making sure this equation is satisfied, right? So this equation links u and v, right? The quantity which, when we, at the very beginning of the class, now you have to take the first or second week of the class, the direct consequence of when we were in 2D continuity equation was that you could define a stream function, right? And that's so we can no longer define the potential, of course, because the flow is no longer irrotational, right? But you can still define a stream function, and the stream function allows you to link u and v together and just solve for the stream function. Right? If you write everything in terms of a stream function, you already take care of the continuity equation, and then you just have one function to solve for. So that's what we're going to do. In that cases, and that will be the same for gravity waves, in that case, to take directly care of the continuity equations, we'll solve for the stream function. So here we have a two-dimensional planar problem. And so we can write the solution in terms of the stream function. So instead of writing u's and v's, we'll write partials of the stream functions. Let me remind it that u is equal to partial psi over partial y, and v is equal to partial psi over partial x minus. Okay. Now, in terms of dimensions, just note that a stream function has dimensions of a velocity times a length scale. Okay, so those are the dimensions of a stream function. This is just for later on. So instead of solving for u and v, we'll solve for psi. And now the method that we'll use is we'll try to find a solution to the velocity field, so to u. You can think of u in terms of a similarity solution. So we'll try to find a similarity solution. Now, let me tell you a little bit about the motivation of why you would think of doing a similarity solution. So you have your incoming flow. Now we've already discussed the shape roughly of the boundary layer. We know it's going to grow roughly as a square root. So delta here grows with the square root of mu x divided by u. Okay, and now let's say we no longer say we have a plate of a certain length L. Right? We're just looking at an infinite plate now. This is an infinite plate. Okay. This is an infinite plate, and therefore, we are looking at the velocity profile at a given point x. Right? So we are giving at a given point x. We want to know what the velocity profile is, and we expect something. We expect something like this, which is boundary layer like looking. So that's our question. What is this? This is just to frame things. This is what we're trying to find. What is the profile in the boundary layer of the u velocity, for instance? Once you have that, you can compute the shear stress. If you have that, you can compute mu partial u or partial y, and you can compute what the drag force is on the plate, for instance. This is why you want to know this velocity. Now, it might not be clear to you, but for the applied mathematicians, this might be more clear. If you have an infinite plate and you're looking at the profile at random x here, right? There is no inherent length scale in the x direction. You no longer have an inherent length scale. You have one diffusive length scale here, right? If you divide everything by delta, then you no longer have an inherent length scale, so you may think about looking for a similarity solution, right? Usually when you have no inherent length scale, like infinite plates, then you have a chance to find a solution which is a similarity solution. No, I'm not an applied mathematician myself, right? So usually when there is one, mathematicians will tell the engineers that there might be a similarity solution. So that's sort of the hint that this is how, why you would want to do that. So let's put all of our dimensions. Let's think about this profile. We have the velocity at infinity u, right? All of our parameters to solve. We have delta, which is the boundary layer thickness here, right? We have the position in y. We have psi, our stream functions, right? And so we're going to try and find a solution. We're going to try to find a similarity solution. So we have to find our similarity variable, and one variable which makes sense is y divided by delta. This is a variable which makes sense. If you want the similarity solution, you already got a feel from just reasoning physically, right? Thinking that the vorticity which is created here now diffuses and is advected. Right? So at every single position in X, you sort of expect that if you rescale the problem, it would look like this. It's almost the same problem as downstream if you rescale with delta. Do you see what I mean? That's sort of mathematically, this is where similarity solution comes from, right? So this is your similarity variable. We're going to try to write everything in terms of eta equals to y divided by delta. So y divided by delta is nothing else but the y location within the boundary layer, right? So in here. And then we need to non-dimensionalize psi. So we have two non-dimensional groups. So let's take our other non-dimensional group here. So this is P1. P2 is when we non-dimensionalize psi, and the only, so psi has length scale of u times a length scale. And if we want to write everything in terms of our, one way of non-dimensionalizing psi would just be to non-dimension by u times delta, right? And so finding a similarity solution is essentially finding psi, finding a solution in the form of pi 2 as a function of pi 1. Right? Nothing, there is no dimensions anywhere. We rescaled the problem, so there is no longer any intrinsic length scale, and we just find the solution that way. So we're trying to find a solution for psi u divided by delta is equals to a function of our similarity solution. Now this is not maybe intuitive, but this is essentially how we're going to try to solve the problem. We try to find a solution of this form. Now, if ever you had to find a solution under this form in an exam, that form would be given. Right? So finding, rescaling your problem to find a similarity solution, that would be, more the subject of an applied maths class than an advanced fluid dynamics class. Right? So all of the mathematical reasoning to get to that form, once you got to that form, it's still mathematically a bit tricky, but the whole reasoning is done. Right? If the solution exists, if you did that right, then you find a solution. But of course, applied mathematicians would do that a lot. Let's try and find this solution. It doesn't work. Let's try to find a solution of this form. It doesn't work. In your textbook, you only get to see the cases where it did work. But before you come up with this, there was a lot of trial and error. Before you were able to find it. So there's nothing trivial about finding a solution into that form. And the only reason why I write it down is because I already know that this is going to work, right? And that is, I only know this because people have spent a lot of years trying the things that didn't work. So this is just to make you realize that there's nothing. If you're a bit confused at this point, there's nothing surprising about that. So we'll try to, but now we have this, so now we'll try to find a solution for psi. So psi now is a function of eta, right? And this is going to be equal to u times delta times a function of our similarity variable, which is y, which is eta, which is y over divided by delta. The only problem is that now, of course, we're writing the whole problems in variables which are not x and y, and all of our equations are u, v's, x and y's. So we need to rewrite everything. So if you look back to those equations here, right? So now what we have, if we have u's, we have a u here, we have a partial u over partial x, we have a v, we have a partial u over partial y, and we have a second partial of u with respect to y squared. So we need to express all of these in terms of our new framework. So this is where, that's essentially just testing if you know how to differentiate. So we need to find u. I'll do a few of these, and then the others, I'll let you do them at home. So you need to find u, you need to find v, we need to have partial u over partial x, we need to have partial u over partial y, and we need to have partial u over partial y squared. Once we've expressed all of these in terms of our new variables, then we can put them all into an equation and see what equation we get. So what is u? I'll do u. U is partial psi over partial y. Right? And you already see the difficulty here is because we have psi as a function of eta. Right? So this is then, I'll do this in blue to not confuse anyone. And the chance that I do a mistake is high. So I have to do partial psi. I have to do partial psi over partial y. So you first have to really look carefully what is the function of y here. So partial psi, partial y. So u is not a function of y. So this I can write. Delta is a function of y. So this is, I'm going to have a partial delta over partial y times the derivative times delta prime. Delta is a function of y. Hold on, am I already making a mistake here? No, let me just take delta. So delta is equal to, oh no, delta is not a function of y. Delta is a function of x. See, I already get it wrong. Let me just write everything because then I'm going to confuse myself. Remember that delta is a function of x, and it's equal to the square root of mu x divided by u, and eta is equal to y. So eta is a function of x and y because it's a function of y here, and it's divided by delta x. So I already made a mistake. But none of you stopped me, so I guess you might have done the same one. So delta is not a function of y, so u times delta, this is fine. And now I have f, so I need to differentiate this with respect to y. The only bit in there that depends on y is eta. So I'm going to have partial over partial y of eta divided by delta times f prime. Right, this is my chain rule. Chain rule. Huh? What? Oh, this is y. Oh, this is eta. Sorry, this is a y. Sorry, my own writing is bad now. So this is eta. Okay, so see, this is when it goes bad. So okay, so let me just rewrite everything. I had a bad start. Yeah, because I wrote two different things. Okay, so. This is really what we have here, okay? Psi is going to be u times delta. Delta is a function of x times f, eta, and eta is a function of y and delta, of x and y, okay? So you're right, so this is terrible. But, it makes you feel better about being confused. So this is u. So if I'm looking at this, u is not a function of y, delta is not a function of y, so f is a function of y because eta is a function of y, so you could think of this as a function of y, so you have to use the chain rule. So this is going to be partial eta, partial y times f prime, okay? and partial eta with partial y, right, is just going to be 1 over delta, right? Because eta is equals to y delta x. So this is going to be equal to u times delta times 1 divided by delta times f prime. So this is equal to u times f prime eta. Okay, so we have u. This is what u is equal to. Now we need v. So v is equal to partial to minus partial psi over partial x. Now hopefully this one is going to go better now that my notations are written correctly. There we go. So v is equal to minus partial psi over partial x, right? So I have to look what is depending on x. Both this term and that term depend on x. So it's going to be minus u, let me keep that, times delta prime, right? So this is the derivative of delta with respect to x times f plus delta times partial f with respect to x. So this is going to be partial x of eta times f prime. And now what is partial eta with respect to x? This here is going to be minus y times delta prime divided by delta squared. Right? I just have to differentiate eta with respect to x. So 1 over delta x is just, the derivative is just minus delta prime divided by delta squared. So this is what that is. And so if you put everything back together, you get minus u delta prime times f plus minus y delta prime divided by delta times delta. Yeah. No, because I already cancelled it, times f prime. Okay, at this point I'm going to look at my notes and see if this is correct, because chances are it is not. Yeah, that looks fine. And so this is an eta, so this is equal to minus u times delta prime f minus, so y divided by delta is eta, so eta delta prime f prime. And of course delta prime is going to be a 1 over square root of x, because we know what delta is as a function of x. Now I will spare you all of the others, I'll just write them for you and you can practice at home. So partial u over partial x is going to be equal to u times the second derivative of f times minus y delta prime divided by delta squared. Partial u over partial y is going to be equal to u times f double prime as a function of eta times 1 divided by delta. And the second partial of u with respect to y is going to be equal to u times the third derivative of f 1 divided by delta squared. Okay? So just do them at home just to practice. It's really just, these are only chain rules. It's chain rule and differentiation. So there's nothing, there's actually, it's just really being careful in all your derivations. And you should be able to get there. Good, so now you replace everything into the x momentum equation. So we'll do that. But there's an important thing that comes out, is that what you would be interested in, which is u, for instance, u, the velocity in the x direction, is a function of f prime. So really what you're interested in is not f, but f prime. And that's sort of logical, because f relates to the stream function, psi, but you're never really interested in the stream function psi, you're interested in the velocity, which are derivatives or partial derivatives of the stream function. That's sort of similar here, right? So you don't really care about, your stream function is always defined to a constant, and that's the same. Your function f here is defined to a constant, and what you're really interested in is the derivative of that function f, which is f prime. That will give you your profile, the shape of your profile. Okay, so we have to plug, so insert in the x momentum equation, u over partial x plus v partial u over partial y equals to, with a rho, equals to mu partial u squared partial u over partial y squared. Okay, and when you wow, this is going fast. So you do this again. You have all of the expressions, so you put all of that in, and what you get is an ODE for f. So the third derivative of f divided by delta plus 1 over, hold on, actually there's simple forms now, so forget about that. This is again an exercise for you. The ODE you get in the end is this. So the third derivative of f plus 1/2 of f double prime is equal to 0. This is essentially everything which applied mathematicians do, which when you have a complex PDE, you try to do something clever to make it an ODE, because ODE are simpler to solve. Now actually, this ODE is not that simple. It screams third order ODE and nonlinear, and you have a nonlinear term here. There's f times f double prime. So again, don't expect any of the tricks you've learned to give you a solution to that ODE. It's just too complicated, and you actually have to solve it numerically, right? But the whole point here is that this is what people in applied math do. When you're trying to solve a PDE, you do something clever to make it become an ODE, which you can solve. So here you do have an ODE. It's a third order ODE, right? And of course, you have to solve it subject to boundary conditions, and that's the key thing. So we have to impose the right boundary conditions here. Now, what are our boundary conditions? Our first boundary condition is that u be equal to 0 at y equals 0. This is essentially why we are doing everything. All of this hard work is to be able to apply the no-slip boundary condition. So we want to make sure that when we solve that, we impose the right boundary condition. Now, of course, you impose the boundary condition here in terms of our initial variables. So we have to look how that translates to in terms of our new variables. So you see, if u is equal to 0 at y equals 0, that means that u, which is equal to u f prime eta, is going to have to be equal to 0 when y is equal to 0. But eta is equal to 0 when y is equal to 0. Eta is y divided by delta x. Right? So this is the same as saying that, so this is equivalent to saying that f prime at 0 is equal to 0. Right? We have to rewrite the boundary conditions in terms of our variables. Is that clear? This is just writing that u is equal to 0 at y equals to 0. And the other thing is that we want u to be equal to capital U when y goes to infinity. Okay? So u equals to capital U when y equals to infinity. How does that translate to? So u, and that is just to say that outside of my boundary layer, I have my velocity at infinity. Right? So what is that? Then when y goes to infinity, eta goes to infinity as well. And therefore I need to have f prime of eta equals to 1 when eta goes to infinity. Yeah? So just do it again when you're at home. F prime when y goes to infinity is equal to 1. Okay, you have those two conditions on the derivatives. And now you have a third order ODE, so you need, of course, three. You always need three conditions, and you have a third order ODE, you need 3 conditions to solve. The next one, which I'm going to do, it doesn't really matter. I'm just going to say that f at 0 is equal to 0. I don't really care about f anyway, right? It's like just it's just identifying the constant of your stream function. That's the same thing as what I'm doing here. Right? So this is here, just, this is unimportant. You know, you can think of it as f as being a stream function, so it's defined to a constant. Okay. Unfortunately, my time is up. So I will finish that really quickly on Tuesday. But I think it would be good if you read through 10.3. Right? It does exactly what we did, and then it plots the Blasi solution. Okay, so you can have a look at the plot, and I'll show you how you can actually compute that. So, but do read chapter 10.3.